Well, we're going to next get into this chapter on light. And you'll notice we skipped a couple of chapters, but that is because light behaves very much as a wave, at least part of the time, which I'll explain that statement in just a second. And so I wanted to do sound and light right next to each other so that we can continue our thinking process of how waves are behaving. Now, sound is relatively easy to understand as far as its properties and its general nature. Light is not nearly as easy to understand, and I don't expect you to grasp all the details, but I do want to try to paint a picture for you of what scientists currently believe about the nature of light. Now, when they first started studying light, scientists like Newton, who we've talked extensively about before with his laws of motion and his law of universal gravitation, experiments that he did as well as experiments that Hertz did, and you'll know that Hertz is the same scientist that our unit of frequency was named after. They did experiments that seemed to show that light behaved as a particle or as a small piece of something. They didn't think that it behaved as a wave. And the reason they thought this is because they noticed that when they would bombard certain metals with light, depending on what color of light they used, that there were some colors that would make electrons escape from the metal, and there were other colors that would not. So their thinking was, okay, it depends what types of light particles we're bombarding that are making these electrons escape. And so some scientists very firmly believed that light was made up of particles. But other scientists were doing other experiments, and they were saying, no. Light behaves much more like a wave if you look at the experiments that we've done. And so if you look at this particular drawing on page 493 in your book, it's this one right here, where you can see this light that's going through these slits. Now, this is not an experiment you would be able to do unless you had something called a diffraction grating, which I'm assuming probably none of you have. I don't have one of those. But a diffraction grating has extremely narrow slits in it. And so what happens is when you shine the light through it, if light were a particle, what you would expect is it would go straight through those slits and make two specific lines on the wall of light behind it. But that's actually not what happened. The pattern, and you can see what happens there, is that as it goes through the slits, it actually splits apart and makes more strings of lights on the wall. And that is very similar to some of the pictures that we saw in an earlier chapter where water waves were going through, like if they had a log barrier and there was a hole in the log, and the waves would go through there, and then they would spread out and they would make other types of patterns as they go through those holes. Well, light was doing exactly the same type of thing. And so scientists like Young and Huygens were looking at these experiments going, no, Newton, you're wrong. Light doesn't behave as a particle, it behaves as a wave. Well, it wasn't until Maxwell came along that he actually realized that light is made up of a disturbance in both an electric field and a magnetic field. And so the picture on the bottom corner of page 489 in your book, which is this one down here in this corner, it shows us that light is made up of two perpendicular waves, and one of them is vibrating an electric field in one direction, and the other is vibrating a magnetic field perpendicular to it, or at 90-degree angles, in this other direction. And so the light is moving in the direction of that black arrow in the picture. So basically, what Maxwell's experiments came to help us realize was that electricity and magnetism are actually two forms of the same thing. And that's why light can travel through a vacuum, is because it doesn't have to have a specific medium to travel through. It's vibrating an electric field and a magnetic field, and those can exist apart from matter, apart from air, apart from water, apart from any type of solid. And so therefore, that's why light can travel through the vacuum of space, because it doesn't have to have a medium to travel through. In fact, when we talked about sound, we said that sound travels the fastest fastest through a solid and the slowest through a gas. It's exactly the opposite for light. Light travels the fastest through a gas and the slowest through a solid. It doesn't have to have that stuff to be able to travel through. So make sure that you get that point there, and that's that light travels fastest through a gas and the slowest through a solid, which is exactly the opposite of sound waves. It wasn't until Einstein came along that we came up with the idea behind wave-particle duality. And again, big words, but really what it means is that light waves actually behave as both a wave and as a particle. And Einstein said that what he believed was that these waves were traveling in, or the light was traveling in little packets. And so since you had a packet and a packet and a packet, that would describe the particle portion, but each packet was made up of waves, and that would describe the wave portion. Now, if all of that is kind of going over your head, you shouldn't feel bad. You're in really good company. A lot of us don't understand this concept very clearly. You have to be super, super smart to really get a really great handle on it. But what I do want you to understand, aside from the fact that light travels faster in gases than it does in liquids and solids, here's the other main point. Light behaves both as a particle and as a wave. We're going to do a lot of our analysis of light as though it behaves as a wave, but there are also times where it behaves as a particle, and so that's our current understanding of the nature of light. Now, as we continue to do more experiments, the model that we've constructed here may fall apart on us, and we may say, okay, well, that wasn't right, and we have to go back and fix it and redo it. But for right now, all the experiments that we're doing seem to fit well with the concept of the wave-particle duality. Everything fits, and until we find something that doesn't fit, that's probably what scientists will continue to think until we have some other evidence to the contrary.